So here is question number 41. The ratio of nuclear density of two nuclei of mass number 27 and 64 will be what? So we are having four options. We know very well the nuclear density rho can be written as mass of the nucleus and its volume. Nuclear mass can be written as total number of nucleons multiplied by mass per nucleon. So total number of nucleon will be mass number. Volume will be 4 by 3 pi r cube. So therefore density will be given as m into A, where A is atomic mass number. 4 by 3 goes at numerator. Pi, r is given as r naught a to the power 1 by 3 whole cube, where A is atomic mass number. Once again I am telling you, 3ma whole divided by 4 pi r naught cube multiplied by A. We got nuclear density rho as 3 times m divided by 4 pi r naught cube. So all of them are constant and it is independent of mass number. Once again I am telling, the nuclear density is independent of mass number. Therefore we can write nuclear density independent of mass number A. So that's why their nuclear density will be same. Ratio will be 1:1. So we will go with option number 2. Now let us proceed to the next question, that is question number 42. So here we are having question number 42. The nucleus of X84-220 originally at rest emits an alpha particle with speed V0. Then the speed of daughter nucleus will be what? Now here law of conservation of momentum will be applied. So according to law of conservation of momentum, initial momentum must equals final momentum. Initially it was kept at rest, so momentum will be 0 and alpha particle has mass number 4. So mass of alpha particle 4, speed of alpha particle V0. Let's write it in the vector form, plus mass of rest of the particle will be what? Total, that is 220 minus 4. Suppose the speed which the daughter nuclei is moving is V. So in vector form we can write it V. So finally we have got the vector V value as minus 4 upon 216 V0 vector. The speed V will be 4 by 216 V0, that is V0 divided by 54. And after looking at the options, we can say that option number 3 is absolutely correct. So we will go with option number 3. Now let us proceed to the next question, that is question number 44. Here is question number 44. The number of nuclei of radioactive sample becomes 1/8 part of its initial value N0 in period of 6 years. The mean life in years of the radioactive sample will be what? Now we know very well, amount remaining after n half-lives given as amount remaining after n half-lives will be given as n equals n0 1 by 2 to the power n, where small n is number of half-lives. N is 1/8 of original, that is n0 upon 8 equals n0 1 by 2 to the power n. After solving we get the value of n as 3. Means during the duration of 6 years 3 half-life has been covered. Therefore half-life will be, that is T half will be 6 upon 3, or you can say 2 years. But we have to calculate mean life. We know very well that mean life is given as 1 by lambda, where lambda can be written as natural log 2 divided by t half. T half goes at the top. The value is 2 of t half divided by ln 2. So 2 upon ln 2 is mean life in years. So after looking at the options, we can say that option number 4 is absolutely correct. So we will go with option number 4. Now let us proceed to the next question. That is question number 44. Here is question number 44. The binding energies of nuclei of element P and Q are EP and EQ respectively. Two nuclei of element P fuse to give one nuclei of element Q, and this fusion process is accompanied by the release of energy. Then EP, EQ and small e are related to each other like what? We know very well energy released is, that is E, given by the binding energy of product minus of binding energy of reactant. So binding energy of product minus of binding energy of reactant. So therefore E, which is already given in the question, that E energy is released. So E is equal to small e, which is further the binding energy of product. Now product is one nuclei of element Q. So energy of EQ given, minus reactant is 2 nuclei of element P. So 2 times binding energy of P, that is EP. Now we can write EQ as 2 times EP plus small e. So this is the relation we have got. After looking options, we can say that option number 4 is absolutely correct. So that's why we will go with option number 4. That is 2 EP plus E equals EQ. Now let us proceed to the next question. That is question number 45. Here is question number 45. Two radioactive sample having decay constant 12K and 4K respectively. If they have the same number of nuclei initially, the ratio of respective number of nuclei after time 1 by 4K will be what? The remaining number of nuclei, we know very well, is given by n equals n naught e to the power minus lambda t. Now it is given that both have equal number of nuclei initially, so we can say that the number of nuclei after any time t is depending upon e to the power minus lambda t. Now for the two cases, case number 1, number of nuclei suppose n1, which will be proportional to e to the power minus lambda is 12k and time is 1 by 4k. Similarly, n2 will be given as e to the power minus lambda is 4k and time is 1 by 4k. Taking the ratios, we'll get directly n1 upon n2 as 4k will be cancelled by minus 3 times, and here 4k will be cancelled with just 1 time. So you will get e to the power minus 3 divided by e to the power minus 1, ultimately e to the power minus 2, which is equal to 1 by e square. So the ratio of n1 is to n2 will be 1 by e square. So that's why we will go with option number 2, which is absolutely correct.